Okay, hello and good morning, Victor, Neo, Trisha, and Neil. Um, okay, so today I think we'll formally close the course right now. I mean, in terms of discussions, because parang tapos na nga natin yung truncated singular value decomposition last time. Of course, there's more depth to it. There are more mathematical theories behind the truncated singular value decomposition, how to optimize the calculation of the decomposition, because you might recall that the truncated singular value, or basically the singular value decomposition to begin with, is a way of writing our matrix A in terms of a product of three matrices, right? The matrix U, the matrix sigma, and the matrix V transpose or V conjugate transpose, where U and V are unitary matrices, meaning that their inverses are their conjugate transpose. Now, medyo mahirap theoretically mag-compute ng SVD decomposition. You will see some matrix decomposition methods in Math 175, or if you have taken 175, alam niyo na yung LU decomposition. Meron pang tinatawag na QR decomposition, may Cholesky factorization, Doolittle factorization, and such. So it's like a whole kind of forms, yung pagpa-factor ng isang matrix or writing matrix in terms of a product of some desired matrices or matrices possessing some desired characteristics. Now, yung SVD ay isa sa kanila, and SVD is one of the most difficult ones to perform because napaka-intricate or napakalaki ng requirement natin dun sa mga components ng matrices kung saan gusto nating masulat or with whom we want to write our matrix A as. So nandun yung dapat unitary sila, tapos dapat yung matrix sigma mo, dapat yung diagonal entries are arranged by their significance. So yeah, it's a little bit difficult to deal with everything, but I think the intricacies, the details behind singular value decomposition is properly addressed in a course in linear algebra. So either Math 120 or AMAT 105, or a special course in numerical linear algebra. When I took a numerical linear algebra course during my PhD, parang ang tagal naming nag-discuss ng singular value decomposition. Kasi kailangan naming humanap ng mga efficient algorithms kung paano makuha yung singular value decomposition. And but luckily for us, for not so big matrices, pwede na tayo mag-rely dun sa algorithm na built-in kay Matlab. And I have shown you the program last time, which we will revisit today. Andali, one-liner lang siya, SVD of something, of the matrix. Yun lang, tapos ibibigay niya na sa atin yung tatlong matrices na kailangan natin para dun sa decomposition. Okay? So that's why, and then we discussed last time the implication of the singular value decomposition to inverse problems. And I guess I really love the reactions that you submitted. I read through those submitted via Canvas before the deadline. Those who submitted after the deadline via email, babalikan ko yung submissions nyo within the week or over the weekend. But yeah, most of you got the idea. The lingering questions or question in their minds is paano siya marirelate dun sa inverse problem. And I hope that the discussions we had last time shed some light to your questions like that, because essentially, ang ginagawa natin sa singular value decomposition, sinusulat natin yung matrix. If I can go back to our notes last time. Where is that? Okay, so essentially in theory, we are simply writing the matrix in terms of this matrix product, right? U sigma V conjugate transpose. Pero ang kagandahan nito ay pag in-expand mo to, ang diagonal entries kasi ni sigma I equals sa singular values, sa tinatawag natin na singular values. And the nice thing about singular values, they are in decreasing order, meaning the singular values can be thought of the weights associated with the dot product of the columns of U and V in terms of representing A. So parang hinahati natin yung decomposition na to, hinahati niya si matrix A into nagbibigay siya ng isang expansion, isang summation para kay matrix A. And the nice thing about this decomposition as a sum, or its expansion as a sum, ay yung mga addends, yung mga terms dun sa ating summation is arranged in terms of their contributions to the exact character or the exact way of how A looks like. So essentially, tinignan natin. So si A, via the singular value decomposition, can be written as this summation. Okay? So summation to ng mga matrices. So each one of these are matrices of the same size as the matrix A. So bawat term dyan. So pwede nyo tingnan bawat isang term dyan, bawat isang matrix na nandun sa expansion as a building block of the matrix A. So if you want to get the exact matrix A, then you consider all of the non-zero terms, which is essentially captured in this expansion because lahat na ng lalampas dito sa art column ng sigma ay wala ng contribution. So ibig sabihin, ito lang talagang R terms na to, where R is the minimum between the number of columns and the number of rows, or hindi pala lagi siya yung minimum. R is bounded above by the minimum between the number of rows and the number of columns, ay makikita natin ano yung mga kailangan nating ingredients para makuha si matrix A. And these ingredients are in decreasing order. Ibig sabihin, itong unang matrix na to, ito yung may pinakamalaking contribution kay matrix A. Second most significant in the building of A is the second matrix, and so on until you get to the last thing. So if you want a low rank approximation, yung rank meron siyang connection sa dimension ng column space ni A. Pero if you haven't taken linear algebra yet, just ignore what I'll say in the next two sentences. But if you took linear algebra, you know what the rank is. So posibleng malaking rank ni A, and it has a number of implications, especially in the computational aspects of the matrix A. But if you're saving on space, if you're saving on calculations expense, so you can approximate A by a low rank matrix. So imbes na rank R, yung matrix mo, kalimutan mo lang yung mga masyado nang nasa dulo ng expansion to get a lower rank representation. So the rank of your representation or approximation to the matrix A will have rank less than R. And that's fine because dito ka naman magta-truncate sa dulo. Ang sabi natin, ang singular value decomposition, binibigay niya rin sa atin yung order of priority o yung amount of significant contributions ng bawat matrix dito sa summation in the building of A. Meaning if we choose to truncate matrices towards the end of the expansion, then we are still getting a good approximation to A. All right? Huwag kayong magta-truncate sa unahan. Kasi pag tinruncate nyo si A, nawala na yung pinaka-significant building character ni A, so hindi na maganda yung approximation. Kaya dito tayo sa dulo nagtatanggal. Well, it makes sense if you're dealing with the matrix A. Pero hindi nga naman obvious kung bakit yung truncated singular value decomposition ay nagagamit sa inverse problems. Kasi kung halimbawa, you're doing computations with the matrix A, then it makes sense that you approximate A by a low rank matrix. So you will truncate some of the terms towards the end of the summation. And then you can work on that smaller matrix. I mean, not smaller in terms of size or dimensions, but smaller in terms of rank. That lower rank approximation to A in performing all the computations. And it makes sense. Makakatipid ka ng storage, makakatipid ka ng computational resources. Pero paano siya magagamit sa inverse problems? Well, our analysis last time, nakita natin, ang daling kunin ng X star. Kasi nga, pag meron ka ng singular value decomposition na U sigma V conjugate transpose para kay matrix A, ang dali niyang kunin ng inverse. So, ang inverse niya na lang ay V, tapos pseudo inverse ni sigma times U conjugate transpose. Right? And then, nakita natin na yung sigma pseudo inverse, as long as the diagonals, or actually, assume na natin na non-zero yung mga diagonal entries ni sigma, ay reciprocal lamang ng mga entries ni sigma yung nasa sigma pseudo inverse. So essentially, you'll have a set of numbers which are the reciprocals of your singular values. Sila yung nasa loob ng sigma pseudo inverse. So now, kung kanina, decreasing order yung mga singular values, ngayon naman magiging increasing order yung mga reciprocals nila. And it plays a big role when we try to compute for what's the effect of a small noise when added to the right-hand side of the equation, which is basically our problem sa inverse problems. Ito yung napakalaking consideration na ginagawa na natin. Kasi nga inherently ill-posed in the Hadamard sense yung inverse problems. So, we tried to do everything on paper first to get the sense of the theoretical analysis. So meron kang AX equals B plus epsilon. Then we applied A inverse to both sides. We already know that A inverse is V sigma pseudo inverse U conjugate transpose. We multiplied it to B plus epsilon. And then we get this expression. And we compared it to the solution that we got from the true data, from the perfect data, from the non-noisy data. Kinuha natin yung L2 norm. Nakita natin, ito yan. This guy, this will be it. And then we simplified. We use Cauchy-Schwarz inequality here. Tapos we use the fact that this guy and this guy are unitary matrices whose L2 norm is equal to 1 kasi ang columns ni V at saka ni U ay orthonormal basis para sa kanilang respective R to the N spaces. So itong norm na to ay 1, itong norm na to ay 1. If you haven't taken linear algebra, forget what I said. Just believe me that the L2 norm of these two guys are equal to 1. And then we'll get this guy. And basically, we said that the L2 norm is basically the largest singular value. And the singular values of sigma pseudo inverse are the reciprocals of the singular values of sigma. So ibig sabihin ng L2 norm ito, pinakamalaking singular value ay yung mga singular values natin para kay sigma pseudo inverse ay reciprocals ng mga singular values ni sigma. Tapos, ibig sabihin, naka-decreasing order sila. So, the biggest singular value for sigma inverse is the reciprocal of the smallest singular value of the matrix sigma. So, ibig sabihin, ang L2 norm niya ay 1 over sigma r. So, basically, the effect of the noise to the relative difference of the solution, the relative difference between the true solution and the noisy solution is sigma, the norm of epsilon, the size of the noise amplified by the norm of the L2 norm of sigma pseudo inverse, which is 1 over the smallest singular value of sigma. So, ibig sabihin, pag masyadong maliit yung smallest singular value ni sigma, lumalaki yung L2 norm ng sigma pseudo inverse. So, ibig sabihin, lumalaki yung epekto ng maliit na noise dun sa relative difference between the true and the noisy solution. And so the question, how do we minimize this guy? How do we minimize the effect of this small noise? Well, we need to minimize this multiplier, etong amplifier na to. And one way to do that, ang ginawa nga natin doon last time, hindi ko na i-discuss yung iba pang paraan, pero the easiest way is to use a truncated or an economy singular value decomposition, meaning we truncate, we go back to A, we approximate it by a lower rank matrix, meaning we will be ignoring some of the terms na nandun sa dulo ng expansion ni A in terms of the singular values and the columns of U and V. And that is fine, as we have established before. Pag nag-truncate tayo sa dulo, okay lang yun. Kasi yun yung may mga pinakakakaunti ng contributions dun sa matrix A. Tapos, pag nag-truncate ka na dun, so ibig sabihin makukuha mo yung matrix A hat, which is basically U hat, sigma hat, V hat, conjugate transpose, where sigma hat will have less number of columns. Kasi binawasan na natin yung mga non-zero singular values niya. So, ibig sabihin, mas lumalaki yung smallest singular value ni A hat. And A hat is the one that we are using in our computations, right? So instead na A, pinalitan natin siya ng A hat na mas maliit yung rank. which gives us much more computational savings. Tapos kukunin mo yung inverse niya. Yung inverse niya ay merong sigma hat pseudo inverse. Yung sigma hat pseudo inverse, kakaunti na yung non-zero singular values niya. And the largest such singular value para kay sigma pseudo inverse ay 1 over sigma sub k, where k is smaller than the usual r na nandun sa malaking matrix. So ibig sabihin si 1 over sigma k ay mas maliit kaysa kay 1 over sigma r. So ibig sabihin, minimize na natin yung epekto ng noise dito. Kasi napaliit natin tong multiplier na to. Instead of the full sigma pseudo inverse, papalitan natin to ng sigma hat pseudo inverse by just truncating this expression for sigma. Okay? When I was drafting this lecture, when I was thinking about it, kailan nga ba? Last Monday, parang naisip ko, parang ang dali lang pala ng singular value decomposition. Parang hindi ganito kadali. Nung pinag-aralan ko to, nung nagpi-PhD na ako, ang dami pang mga theoretical derivations, of course, which are important because sila yung nagbigay ng credence dito sa approximation by low-rank matrices, and so on, and the computational efficiency. But if you are not working with very crazy matrices or very large matrices, then I guess ito yung gist ng theory behind the truncated singular value decomposition. And this is very powerful. Hold on, guys. Excuse me for 30 seconds. Sorry about that. Runny nose emergency again. Kaya ito yung problema ko pag nag-face-to-face. Kasi pag medyo magabok, umaatake yung allergic rhinitis. Pangmayaman no? Pag mayaman daw allergic rhinitis. Kapag hindi naman ganun kayamanan, ano lang, anong tawag doon? Sipon lang, ano. But anyway, sorry kung may nagbe-breakfast dyan. Pero yon, where am I? Napaka-powerful ng singular value decomposition because even during my PhD, when we're doing research, nag-work kami sa control ng sound. So how do you control sound in several environments? Halimbawa, sa free space, which is basically, halimbawa, walang obstruction. So yun yung free space. We did it in the underwater environment. So halimbawa, isang ocean na homogeneous yung behavior, ibig sabihin, constant yung temperature, constant yung density ng water, constant yung salinity. Pwede rin sa shallow water environments when you have an ocean with 2 layers of different characteristics. We also try doing it inside 2 different materials. Tapos, gumagamit kami ng Tikhonov-Morozov routine. Kaya lang hindi laging maganda yung binibigay sa amin ng Tikhonov-Morozov routine kasi hindi nagko-converge yung paghanap namin ng alpha, which is like the failure of the L curve dun sa dalawang examples natin sa klase, the heat propagation and the convolution problem. Pero kinailangan namin maghanap ng iba pang regularization routine, and oddly enough, yung singular value decomposition or the truncated singular value decomposition gave us somewhat better results in some cases than what we have from Tikhonov. Ang problema lang talaga namin sa singular value decomposition, napakamahal niya computationally. Ginagamit pa rin namin yung SVD ni Matlab kasi ang ganda na nung design nung SVD routine ni Matlab. If you look at its documentation, the computations is there. Isa na siya sa mga pinaka-efficient na paraan to do it. But our problem is that we're dealing with large matrices. Usually, meron kaming 30,000 by, say, 6,000 matrix. So it's a very tall and slim matrix. Tapos imagine kung ipapa-SVD mo to kay Matlab. Tapos, syempre, dahil hindi namin mahanap right off the bat yung optimum number of singular values, kailangan ad hoc yung pagpili namin. Halimbawa, dapat yung singular value ay hindi pag lumampas na yung singular value by, say, 10 to the minus 6, itatruncate na namin siya. So parang ganun yung criteria, and it's trial and error really to find that optimal ending R sub alpha or the K that we are using, Pero yeah, essentially it's really powerful. It's very simple yet very powerful. So any questions about that? Naka 20 minutes ako ng recap, no? But I hope you appreciate the singular value decomposition, and I hope this discussions answered what you wrote in your reaction papers. Maganda sana kung yung reaction papers ginagawa niyo live, Kasi ayaw niyo naman magsalita sa klase, pero maganda sana. I really appreciated your answers there. Para dun uli sa mga nagpasa via email, ziniro ko na muna kayo dun sa Canvas, pero I'll go back to my email and then isa-isahin kong i-check yung mga submissions nyo, probably over the weekend. So huwag kayong magtampo kung ziniro ko na kayo. Babalikan ko yon, Ziniro ko lang siya para hindi ko makalimutan later. Any questions? Tapos napansin ko pala, parang I was, kahapon ko lang kasi na-upload yung recording. I forgot to upload it last Tuesday. Tapos para palang sounding lata ako nung last meeting. I hope my audio is better now. Hindi ko alam kung anong microphone yung naka-activate last time, but I hope my audio is good now. Okay, so no questions? Okay, so I think now let's just revisit the code one more time para ipakita yung utility again kung bakit ko siya pinili na isulat as a function, as an external program. Have you guys tried using the code, that code or any of those external functions that I shared with you? Kasi lalo na if you're beginning with Matlab, it might be a little bit intimidating na gumagamit ka ng external subprogram. Kasi dati, meron lang tayo isang main program, doon natin ine-encode lahat. Pero may mga routines kasi na gusto mong i-call na lamang whenever working in another code. And then you don't want to write or copy-paste an entire block of code from one small code to a bigger one. Kasi ang mangyayari doon, kakailanganin mo pang baguhin yung mga variables na ginamit mo doon sa ika-copy paste mo doon sa big program. Because once you write one big script, dapat consistent yung mga variables. Dapat wala ka nauulat na variable na unintended. Kasi kapag ka doon sa kinopy paste mo na part, ginamit mo na yung variable say x and na-assign mo na siya doon sa taas, and those two x's are meant to denote two different things, then your program will fall apart. So yun pa yung isang malaking problema. Kaya mas okay kapag meron kang isang routine na feeling mo magagamit mo in some other programs, mas okay na isulat mo siya as a external program or as a subroutine. Okay? So let me share my Matlab screen now. Siguro tingnan lang natin yung pag-i-integrate nung TSVD deconstruct or TSVD reconstruct as part of a bigger code. Okay? So remember, if you go to the TSVD reconstruct.m, merong function sa simula ng program, ibig sabihin ito ay isang external routine. It's an external program. And then it will output XR sub alpha, which is the solution using the TSVD routine. Okay, truncate na natin yung singular value decomposition to get x sub r alpha. So instead of solving the system ax equals b plus epsilon, we are solving a hat x equals b plus epsilon, where a hat is a lower rank approximation to the matrix A. Okay. Tapos TSVD reconstruct, ito yung gagamitin yung code as if this is a built-in command, basta nasa same folder, yung TSVD reconstruct.m, pwede nyo siyang i-call sa isang mas malaking program. Tapos when you call it, you need four inputs. The matrix A, dapat na pre-compute nyo na yan. Meron kang matrix B. This matrix B is the right-hand side matrix. It could be just the actual B from your problem, or it could be B plus epsilon from your problem, where epsilon is your noise. Basta ipasa mo na kung ano yung gusto mong right-hand side dito, with or without noise. Then R sub alpha is the number of singular values that you want to be kept. So kung gusto mong i-keep yung unang 100 singular values, then your third argument for TSVD reconstruct is 100. Tapos itong graph SVD, kung gusto mong i-graph yung mga singular values ng yung matrix A, put 1 here. Kung ayaw mo naman, put any other number. Usually 0 yung nilalagay natin kung ayaw natin kasi 1 is on, 0 is off. Yun yung logical interpretation or yung binary Boolean characters for true or false or for on and off. So let's see. Now I think last time we did this we wrote this program, try tsvd.m, and this main program calls tsvd reconstruct. So I didn't need to copy paste the entire content of tsvd reconstruct into this bigger code. Kinol ko na lang siya. I just made sure that I saved try tsvd.m in the same folder as tsvd reconstruct para may access siya dun sa folder na yon. Okay? Tapos ito, piling ko lang r sub alpha. Oh, kailangan ko palang i-load yung data ko, no? I-load ko yung convolution data.math. Okay. Tayin lang natin. Medyo loading siya. Nag-iinit pa yung computer ko. Oh, there we go. So I loaded the convolution data .math, and then we got here the matrix A is 64 by 64. So, ibig sabihin, yung maximum R sub alpha natin ay 64. When you put 64 here for R sub alpha, ibig sabihin ay ginamit mo lahat ng singular values. So, wala kang tinruncate dun sa expansion. But we know what will happen if we keep all the singular values, because if I hit F5 here, sana mabilis siya mag-run. And this is my fear. Matagal siyang mag-run. Kaka-on ko lang nung computer ko. Oh, there we go. Tapos problema ko pa yung graphics. Medyo mabagal. So this is what we'll get if we let Matlab use all of the singular values. Problema na naman yung graphics niya. But I hope you can see it, all right? So this is what will happen if we will use all of the singular values. Kasi nga na-amplify nung smallest singular value yung epekto ng noise. Kasi nga yung epekto ng noise ay namumultiply ng 1 over the smallest singular value. I kept all of the singular values, so magkakaroon ka ng mas malaking amplifier, yung 1 over sigma sub r sub alpha, which is sigma sub 64, the 64th smallest eigenvalue ang nakakapag-amplify dito. Nakita nyo, medyo ang laki ng epekto ng 1% noise. By the way, 1% noise yung data natin dito, because here, if we go back, ginamit ko si A, tapos yung second entry niya dapat ay B. But what I want my external subroutine to use as B is data Y plus E. Ito yung na-compute ko na before. Tapos R sub alpha. And then here, graph SVD is 1. Meaning gusto ko makita kung gaano kalaki yung mga singular values. So ito yung graph ng mga singular values. So ibig sabihin, ang pinakamaliit na singular value ay nangyari dito sa dulo. I don't know if I can see that smallest singular value. Naku, kung maklik-click ko siya. Hindi ko siya maklik, pero this is of order 10 to the negative 3. So, ganun kaliit yung mga nasa dulo na ng singular value decomposition. Well, you can just say R sub alpha, say, pwede mo itong palitan. Halimbawa, kalahati lang, 32 singular values lang yung gusto mong i-keep. So, oops, lagyan ko nga ito ng close all. Hindi, okay lang yan. Hit F5, palitan mo lang yung 64 by 32. It ran a little bit faster now. And you see, you have a little better approximation to the actual F coming from the noisy data. Remember, ito ay galing na sa noisy data, and we see a little bit of improvement here. Okay, sa 32. Try natin yung 64. 32 kalahati ng 32, 16. Tignan natin kung gaano kaganda yung estimate na makukuha natin. It's not that good. So meaning we need to push it a little further. Pero makikita mo parang maganda tong 16 kasi medyo hindi ganon ka jagged, hindi ganon ka ka-rough. Ano bang kabaligtaran ng smooth mathematically? Medyo smooth na ngayon. Mas smooth na ngayon yung solution natin nakukuha when you use 16 singular values. So the question is, what is the optimal R sub alpha? Paano natin mahanap yung pinakamagandang R sub alpha para sa ating decomposition? Well, I don't know if there's an easy way to find that R sub alpha. Maybe you can look at the literature. So siguro pagka mag-ESP kayo sa akin tapos kailangan natin ng TSVD, maghanap tayo ng related literature on how to find the best R sub alpha. Ilan dapat yung singular values na i-keep natin, or ano yung threshold para dun sa singular values na i-keep natin. Usually it's a percentage, or it's about the magnitude of the singular values themselves, right? Pero para sa course na to, dahil elementary TSVD lang naman yung gagawin natin, ano? Pwede tayong mag-ad hoc. I-run na natin to sa lahat ng 64 singular values and take note how good the approximation is for each of the R sub alphas. So maybe we can write another program here. Let me just close everything. Close all. Tapos, clear ko ba? Sige, clear ko na lang uli. Tapos, load ko yung data. Okay. Tapos, let me write another program. And this time, the goal of this program is to compare the results for various R sub alphas. So, titingnan natin ano yung mga resulta kapag gumamit tayo pag ginamit natin lahat ng R sub alphas in the spirit of finding the best R sub alpha. Kasi 64 lang naman yung dimension ni matrix A. So meron lang siyang at most 64 singular values. Eh di pa-compute na natin kay Matlab ano yung approximate para sa 64 cases na yon, and let's just pick the best one. All right? So gawa tayo ng mesh para kay R sub alpha. So si R sub alpha, sabihin natin ay from 1 until 64. Okay. So, ganito karami. Or actually, hindi ko na pala ito kailangan kasi 1 to 64. Pwedeng sa for loop ko na siya kagad ilagay, no? For end. So, for I going from 1 to 64, kasi meron tayong 64 possible singular values, ganito yung gagawin niya. So, kukunin ko si XR alpha. Pero I will let Matlab or I will let Matlab overwrite XR alpha kasi hindi ko naman kailangan lahat ng XR alpha para makasave sa memory. Hindi ko naman ito i-call lahat later, so hindi ko na siya isa-save. Papabayaan ko na lang si Matlab na i-overwrite yung XR alpha every iteration. But here, XR alpha will be TSVD reconstruct of, ano yung inputs natin? A, tapos B, ang ating B ay data Y, plus the noise vector. Tapos third entry ay R sub alpha. Ngayon gagawin natin to sa lahat ng R sub alpha from 1 to 64. So gagawin ko to ay I. Para dito nag-iterate yung ating method. So I or R sub alpha will go from 1 to 64. And then isi-zero ko na yung graph SVD kasi ayoko nang makita pa ulit-ulit yung graph ng mga singular values. Kasi otherwise, magkakaroon ka ng 64 na pare-parehas na graphs, right? Kasi ginagraph mo lang naman lahat ng singular values. So I'll put off to that or I'll put 0 to that argument. Lagyan ko lang ng semicolon para hindi every step of the way ay nag-appear yung mga x sub R sub alpha. Halimbawa, kung naiinip ka, gusto mong malaman kung nag-run ba yung algorithm mo, siguro maglagay ka dyan ng display I. Para dun sa command window, nakalagay kung anong iteration number ka na. Para hindi ka naiinip, no? Or para alam mo na nag-run yung program. Pwede ko palang i-share later yung yung progress bar na ginagamit ko. Para kita ko may lalabas sa progress bar na nag-update every iteration. Sinasabi niya kung ilang minutes o ilang days yung kailangan bago matapos yung program. Lalo na kung mainipin kayo, tapos may for loop na ganyan. And then after XR alpha, ayoko makita yung bawat isang XR alpha. Gusto ko lang makita yung mga relative error. how good each of these x sub r alphas are. So ang gagawin ko lang dito ay computing ko yung relative error. So rel error. Tapos is-save ko to sa bawat instance. So dapat naka-save siya in a vector. So is-save ko lahat ng mga relative errors dun sa vector na ang pangalan ay rel error. So tapos nagkakaroon siya ng component I para ibig sabihin yung ith entry niya ay corresponding dun sa relative error dun sa dun sa r sub alpha na equal kay I. Tapos ito, computein ko yung norm ng xr alpha minus yung true solution which I computed before to be f exact. Okay. So just be careful lang uli. I guess I messed up the dimensions of f exact data x and data y from last time. Kaya yung iba sa inyo hindi napansin yon, na-carry siya dun sa problem set. So but note here that in-arrange ko na sila in a nice in the right dimension. Look at my workspace. F exact is 64 by 1, which is expected. XR alpha being the solution to a hat x equals b plus epsilon will also be 64 by 1. So kaya ito ay parehas 64 by 1. So yung result nila ay isang vector lang. So getting the norm is safe. Kasi pag magkaiba yung dimension nila, gagawin siyang matrix ni Matlab. Tapos iba yung pagko-compute ng norm ng matrix kaysa sa norm ng vector. Alright? So be careful with that. Divided by norm of f exact. Tapos, save niya yan. Tapos, i-plot natin yung relative error as a function of xr alpha. Okay? So, let's plot. Ang x components natin ay 1 to 64. Tapos, relative error, rel error. Okay. Tapos, lagyan lang natin ng x label. Ito ay gawin nating latex, r sub alpha. Tapos, kailangan ko ng interpreter. Tapos, latex yung ating interpreter. Okay? Tapos, y label. Relative error. So, sana masayangin niya kayo na dapat insightful yung figures na nilalagay nyo sa isa nyong presentation or sa inyong report. Ano? Lagyan din natin ng title. Anong title lalagay natin? Relative error as a function of r sub alpha. Tapos dahil meron akong LaTeX commands na ginamit, kailangan kong i-declare yung interpreter to be latex. Dapat latex. Okay, so I guess that's it. And then we just need to save this. Just make sure to save this inside the same folder as TSVD reconstruct. Try TSVD2. Save it. Pag save niya siya, run lang natin siya. Sana tama. 5. Okay, so ito yung relative error. Bakit ganun? Mali yung r sub alpha. Okay. Na-OC ako dun sa title. Nawala yung r sub alpha dun sa title. Nakalimutan ko yung backslash dito sa latex nito. Tapos siguro gawin nating yung line width ay gawin nating 2 para medyo makapal yung line. Okay. And then let's press F9 to redo the table. There you go. Here's our table. And then now we can pick saan ko ititigal. Ilang singular values yung ikikip natin based on this brute force search. Siguro para makikita natin, the best one is somewhere here. Okay. When we only have 12% relative error, 12.6 relative error, when we used 57 singular values. Kaya lang, and then you will see here that you will be good. You'll be fine until you use 62 singular values. You get about 14% accuracy. But once you do 64 and 63, medyo may sudden spike doon sa relative error. So here, this suggests that we pick R sub alpha to be equal to 57. Okay? Tapos, alam ko na, nakita ko na, yung 57, yung pinakamagandang gamitin na R sub alpha, balik ako dun sa try TSVD version 1, tapos gawin ko dito 57. And then I'll run this. And then we'll get the following solution, which is a lot nicer than the previous solutions that we have found. Although medyo madaya tong method na to, no? Kasi brute force siya. Kasi tiningnan ko lahat ng possibilities. Tiningnan ko lahat ng possible R sub alpha. Tapos, pinerform ko yung calculations. But at least I found, since this is not a big problem, I found the best one. Okay? So I hope you will have some time to play with this because this will be very important. Because when you do your project, meron kayong isang problem, gusto kong ipakita nyo yung naive reconstruction, gusto kong ipakita nyo yung reconstruction using L-curve, reconstruction using Morozov, and reconstruction using truncated singular value decomposition. And then you compare the three. Okay? So ganun yung maging idea. But we can talk more about the problem, about the final project on next week. All right? So para mas ma-brief ko kayo ng mas detalyado. Okay? Guys, do you have any questions about the Matlab program? I hope it makes sense. And I hope you'll find time to play with it. Swerte nyo nga, binigay ko na yung code no? So, pero hindi naman siya ganun ka-big deal, ano? So if you look at the code, napakasimple lang naman ng bawat line. So it's just familiarization how to write a Matlab code. So, but I guess, I hope that this is a good training for you. Any questions about this? Wala na? Sure. And then for the last, kung walang tanong, for the last segment for today's meeting, I'm gonna share with you, or I'll discuss with you a little bit yung homework, anong tawag doon? Homework 7. Oh, may tanong pala si Victor. Paano if truncated? Which one is truncated, Victor? Alin yung binabanggit mong truncated? Dun sa SVD code. I'm not sure kung merong TSVD na built-in si Matlab, right? Pero dun sa SVD na code or dun sa TSVD reconstruct na code, if we go back to it, let me share my screen again. Okay, so if we go back here sa TSVD reconstruct, okay, so sa line 12, binibigay sa akin ni Matlab yung full SVD decomposition. Again, you can search the Matlab documentation or Matlab help if there is an automated truncated singular value decomposition or economy SVD. I'm not sure kung meron, pero dito minano-mano ko yung paggagawa ng truncated SVD. So sa 12, kinompute niya yung full SVD. Tapos, dito ko in-implement yung truncation sa line 27.